Now to this series. This was everything about sequences on our schedule. So now it's about series, which means that we are summing up certain number sequences. And as you see, this special series is quite interesting. If we just look at the first few numbers inside here, this is always a good idea to, well, to make a guess perhaps, or to say, to get a feeling about what this series tends to do, or just to have a more concrete, yes, let's say feeling about what it is. So anyway, it's a fact that the limit of this summation equals 1. This is what's given here. I call the whole thing S because the summation runs from 1 to infinity. So this is like, you could say this is already a limit been taken. And if a limit exists, I can just call it S instead of giving this one an index. If we use indices, it's usually for the so-called partial sums, which we will also have a short look at then later. But this is starting with 1 and setting it for k. So we have 1 by 1 times 1 plus 1, so it's in the end it's 1 by 1 times 2, so just 1/2. The next one is 1 divided by 2 times 3, then plus 1 divided by 3 times 4, so it's quite an easy scheme, of course, and the resulting numbers are interestingly these ones here, like 1/2 and then plus 1/6 plus 1/12, and then plus, you can easily continue this. The next one would be 1 by 20, of course, and then 1 by 30. Interesting that the distance between these denominator numbers grows a little bit, always in steps of 2. Anyway, at first sight, it's absolutely not clear why this kind of summation should have a limit of 1. Much in contrast to the so-called geometric series, which you also discussed in the case of base 1/2. If you know what I mean, talking about summing up, like, well, if I leave away the 1, which is the neutral, yeah, let's take it into account. 1 plus 1/2 plus 1/4. Always, if I always take half of the previous element, this is probably very familiar to you, I hope so, and it's quite easy also geometrically to prove that summing up in this way will never exceed a value of 2, you know, so that the limit of this one equals 2. You know why? It's like if I always take half of the portion from before, I never fill up my container. There are many ways to visualize this in a geometric way. So it's also really called a geometric series. It's like, well, actually it's an exponential series, a special sort of exponential series or a sequence that is summed up. I want to say that. So the geometric sequence is actually an exponential sequence, but if it converges, if a limit exists, it must have a basis lower than 1. So, or yes, in the positive case, okay, between 0 and 1. So that's familiar. But this one, if I cross out the 1, look, even here, I can say, okay, this is easily shown that now this one tends or approaches 1, but this one, well, it does not have such a simple geometric interpretation. So now why am I telling you this? It's because the only, but yet then I must say a very elegant idea or elegant, let's say, approach to prove this is one by transforming these elements. So here, try a decomposition into partial fractions as simply as possible. And when I say this, I mean, well, you might use the standard scheme for decomposition to partial fractions, but this honestly would be not the best way to do it. It's much easier. I do the following. I just guess. I guess that this fraction is the same as the difference 1 divided by k minus 1 divided by k plus 1. Let's just call it a lucky guess. And if we have this, we can easily prove it by combining these again to be one fraction. So this is what I do, okay? I expand this fraction with a factor of k plus 1. You see, so I take the common denominator, like k multiplied with k plus 1. These are neighboring numbers, so this is the least common multiple, of course. Then I expand this fraction with a factor of k plus 1. You see, k plus 1, k plus 1. So this is 1 by k in the end, contribution. And the other fraction is expanded with a factor of k. So I get k as a factor here, times 1, and here. So that's it. And then I can remove k, k minus k cancels. 1 stays here, and the product stays below. So that's a fact. And since each and every of these elements in this sequence embedded to construct the sum, to construct a series, consists of a difference of two simple natural fractions. We can rewrite this series as to be, firstly, a little cautiously, I would say, let's take a partial sum first. Now I call it Sn, which means I don't sum up to infinity, I sum up just the first n elements, yeah, from 1 to n. And then in parentheses, I write this one, 1 by k minus 1 by k plus 1. And then I look what I get by hand. And then I say, okay, what is the first contribution? Well, it's setting k equal 1 by 1 minus 1 by 2, that's fine. And leave it in parentheses just for clearness, because this difference, of course, is important. Oh, I see. I'm actually, yeah, this seems to be a mistake. It must always be minus between. That's right. Yeah. So, but anyway, the next element, I'm talking about these. No? This 1/2 is now represented by 1 minus 1/2. This one, 1/6, is represented by 1/2 minus 1/3, which you can easily see that's correct. 1/2 minus 1/3 equals 1/6. And the next one then accordingly, well, it's 1/3 minus 1/4. So that's true. But this is the difference, and then I'm summing up. So in the end, if I remove the parentheses, which I may do, I don't even rearrange the elements, I will find that the subtraction here is cancelled by addition in the next term. So minus, I start with 1. The funny thing is that the limit 1 is there from the beginning. It's the first thing I do. I put a 1 here. And then I subtract 1/2 and I add 1/2. I subtract 1/3, I add 1/3. That's next here in the continuation part, okay? And then I subtract 1/4, I add 1/4. So this is like taking 1, then going below, above again, as going down, going up, going down, going up. Sort of, if I would start here and I go down, sorry, what is it? I go down and up, but always in smaller steps. Yeah, it's like, and then I reach my 1 approximately again. That would be a graphical representation of what we're doing here. So now, but to be exact, to be formally correct, I would have to put this in a symbolic form, and the partial sum Sn will be, as you see, the whole procedure will be ending with the element numbered index n of this sort. So the last one will be 1 by n minus 1 by n plus 1. That's it. And so everything cancels except for the 1 here and the subtraction of 1 by n plus 1 here. So that's what I get for the partial sum. And then I can argue that afterwards, S, if it exists, is the limit of the partial sums. You know what we are doing here? We are, you could say that we are putting, searching for the limit of an infinite series, putting it in the form of the limit of an infinite sequence. That's a little bit of difference. You know? So you see, we represent the series by a sequence of its partial sums. That's what we do. And the limit of these partial sums now obviously equals 1. I can apply the limit operation here, yeah, because 1 is constant. So I have 1 minus limit of 1 by n plus 1. And this very obviously approaches 0. because it's the reciprocal of an ever-growing number. So that's easy. That approaches 0. So 1 stays there, and then s equals 1. So that was quite, well, an effort now to find that this is true. And afterwards, please, yes, don't forget what we just found, because this will be very helpful. This result will even be very important for the next exercise.